I would like to welcome everyone to the Alberta Innovates Water Connect series, Managing Urban Water Systems session. Today, you'll hear from Guy Greenaway and Tracy Lee with the Mistakis Institute for the Rockies, Corey Albers with Source to Source, and Edwin Say with the University of Calgary. Their bios are available in your engagement tools. For those of you not familiar, Alberta Innovates is a provincial corporation created to support research and innovation activities. We provide funding programs, advice, connections, technical expertise, and applied research services. Our scope encompasses the whole innovation journey, from generation of ideas through applied testing and validation to commercialization and end use. The Water Connect series will share ideas and outcomes from projects funded through Alberta Innovates' Water Innovation Program. The Water Innovation Program is designed to help achieve the goals of Alberta's Water for Life strategy and Alberta's Water Research and Innovation strategy. The knowledge and technologies developed in this program will help to create a clean tech industry in water treatment, support improvement in water use conservation, efficiency, and productivity, and provide safe, secure, and reliable water resources for a growing population while maintaining the health of aquatic ecosystems. I hope this series will provide you with some valuable information and spark discussion. Now let's get started. I'll pass it over to Guy and Tracy, who will be speaking on their project, Supporting Municipalities in the Ecological Management of Water Systems.
Great, thanks very much, Vicki. Can you just give me a quick thumbs up to make sure you can hear me? Great, okay. And thanks to everybody for participating in this webinar, for coming in and watching. What Tracy Lee and myself, I'm Guy Greenaway, we're going to do is split our presentation in half. Both of us are senior project managers at the Mistakis Institute, and the project that we're presenting on, the Supporting Municipalities in the Ecological Management of Water Systems, is a combination of 4 different projects that we've created to synergistically work together towards a set of goals. And what we'll do is we'll present them each separately, just a little insight into each one of the 4. I'll do the first 2, and then Tracy will do the next 2. So first of all, the Mistakis Institute, for those of you who don't know our organization, we're a not-for-profit registered charity. We're an applied research institute, and we have a formal affiliation with Mount Royal University in Calgary. So our vision is a world where communities have genuine access to the science and research they need to make choices that promote healthy landscapes. And the role that we try and play in that is to make innovative research accessible to communities and decision makers. And by that, we mean truly accessible, not just put out there on a website, but put in a form that they can use. And when we say decision makers, we mean everybody from federal government, provincial government, municipal governments, landowners, industry, whoever is making a decision that has an impact on the ecological health of the landscapes. So the 4 projects that we're going to talk about today, or the 4 sub-projects, are the Municipal Eco Toolkit, the Regional Wetland Data Strategy. I'll do those 2. And then I will pass it over to Tracy to do Call of the Wetland and Amphibian Connectivity in Calgary. So like I said, we've started this off with a large project that brought together a number of different goals and a number of different activities, all working towards that healthy aquatic systems and doing that within the context of municipalities. So when we look at the Synergizing Goals, it's to increase municipal capacity to manage those natural and semi-natural water systems for ecological outcomes, to enhance the community knowledge of healthy aquatic ecosystems in those areas, maintain or enhance the natural and semi-natural water systems within municipal boundaries, and then ensure that all of that resultant knowledge, my slides keep moving ahead for me, ensure that all of that resultant knowledge and the tools are accessible to Alberta municipalities. So our focus is the province of Alberta. So the first one I'm going to describe is the Municipal Eco Toolkit. The context here is that, well, the value of natural infrastructure to municipalities, within municipalities, is increasingly well known. How you identify and maintain the natural systems that underlie your natural infrastructure is less well known. And lots of municipalities are challenged with trying to figure out how to do that. So our goal is to try and create an online toolkit for municipalities that would provide descriptions of a number of different municipal management tools that are available for maintaining natural systems. And we put them under 5 categories: protection, planning, practices, perceptions, and persuasion. And I only had to work really hard on one of them to turn it into a P. All of the rest of them fell in fairly naturally. So the first effort, our first phase, was to focus on the water system natural infrastructure and start to populate the tool with those kinds of opportunities for municipalities. So what we did was an extensive literature review, search of management tools, interviews with a variety of municipalities and municipal stakeholders, surveys, partner engagement, and all of that to try and determine what municipalities needed with regard to natural infrastructure tools. And then we developed the Municipal Eco Toolkit based on that information. So it's a web-delivered toolkit that has information about natural infrastructure, natural systems, the role that they play together, and the role that municipalities have in that, plus a toolkit that has all of the different tools, and like I said, categorized under these 5 different categories. You click on it, it drops down, it opens up the different tools. And right now we'll have all of the basic information for those tools available by the end of this month. So the next steps, like I said, we've completed phase 1, this background research, and developed the initial web tool, and we've started doing the preliminary outreach. It's not a great time to do a launch of a tool, so we'll do the formal launch a little bit further down the road, but we are going to be releasing it in stages, a sort of soft release to a number of our municipal partners. The next step, the phase 2, is we kind of think of it as we've got the 101 the 101 information in the toolkit right now, and the 201 information will have to be added later. So right now we want to kind of keep the resources at a standard level for all of the tools, but ultimately get those increased in terms of the complexity and the amount of information, and also to be able to reach out to municipalities to have them add into it. And then that next phase also includes training for municipalities. So going out to the municipalities in Alberta, a number of them, to actually show them what the toolkit is, how it works, and how they can use it. So that's the Municipal Eco Toolkit. The second project within our program is the Regional Wetland Data Strategy. And the context here was, despite the fact that we all quite widely recognize the issues with wetlands, that they're very important, we're losing them very quickly across the province. I'm not sure if the slides are advancing automatically. Sorry, I'm going to try and keep on top of that. The land use impacts that we have on municipalities, despite all of that, municipalities really don't have access to wetlands data that fits their needs, fits their structures, their planning mechanisms. So the research that we've done through this project and through other projects, the discussions we've had, indicated a real value in trying to collectively bring together a number of municipalities to develop a strategy to secure better wetlands data. So it's not that there isn't wetlands data, it's that we need data in a form that works for municipalities better. So that's the goal. Develop a strategy that will improve the ability of municipalities focused in the Bow River Basin, that's our area of focus for this project, to secure accessible, usable, current, and consistent wetlands data. And in all of our documentation, we unpack all of those words to get a little more detail about what we mean in each of those cases. So what we did, again, surveying municipalities in the Bow Basin, doing interviews with different stakeholders in different municipalities, a number of literature reviews. We did a catalog of all of the available wetlands data sets, and we convened a workshop of the municipalities in the basin. I think we had about 12 of the municipalities represented, created an advisory group of municipalities to help us determine what are the wetland data issues that municipalities are facing, what are the needs that they identify that they would like to have addressed, and then what are some of the opportunities that we might have to try and do that. So we developed a collaborative strategy that would lead to this situation of having higher quality wetlands data. And the intent there, like I said, is to not create something new that doesn't exist, but to create something that works specifically for municipalities, that informs their planning, that informs their wetland protection efforts, and that informs, in particular, their wetland restoration efforts, but all in the municipal context. So all of the information that was created is located on a website, the wetlandsdataworkshop.ca website. So all of our background research and the results of our workshops. And then we've now just finished the draft of the strategy, which includes a number of proposals to municipalities, proposals to the government of Alberta, and messaging, basically all of the pieces that are going to be needed to create that kind of a go-forward strategy. Our next steps, we're actually quite pleased. I think we're about 98% sure that we've secured about $500,000 that we need to develop the Bow Basin wetland data sets. And those data sets would include a current wetland inventory, a drained wetland and drained and impacted wetland inventory. And that's basically the restorable wetlands where the municipalities can prioritize their efforts, an historical wetland inventory, and associated with all of that, a wall-to-wall land cover. And these data sets are integrated data sets, even though they represent different things. And then part of the proposal is to the government of Alberta to renew that current wetland inventory every 3 years so that municipalities can reliably expect that they can see that information be brought forward in a current form at least every 3 years and not get into the situation that they are now, where we have some areas that have current data, some that have less current, some that have high resolution, some that have low resolution, but again, provide that consistent, usable, accessible, and available information for municipalities. So with that, I'm going to turn it over to Tracy.
Hi, everyone. Thanks very much, Guy. So as Guy mentioned earlier, I'm going to talk about the Call of the Wetland program, which was a citizen science project that monitored amphibians in the city of Calgary. And then I'm going to talk about amphibian connectivity project in the city of Calgary, which stemmed out of the Call of the Wetland program. So the objectives of the Call of the Wetland program were to actually very simply understand from a biodiversity perspective which amphibians occur in the city and where they are occurring. And then the second goal was to engage Calgarians in urban wetland activity. So hopefully through experiential learning of monitoring at urban wetlands, they would get out and visit them, learn about them, and understand their incredible value. The methodology was that we picked 54 wetlands around the city of Calgary that are all publicly accessible. And we developed methodology for surveying at night and in the day. And we trained people on how to survey for amphibians. They would record their information through a smartphone application, and this was designed specifically for the project and enabled people to register for a specific wetland in a time period that they would survey. It would remind them of the identification of the species and the sounds of the different species that occur in the city of Calgary, and they could fill in whether they saw something or not during their survey. They were also able to take photos and record the sounds that they were hearing if they weren't sure what they had seen. So this was a 3-year project. So we had citizens out collecting for 3 full amphibian seasons. We had over 200 people participate, and they undertook over 1,000 amphibian surveys, which is quite remarkable if you think about it. Each wetland was visited 6 times per season for survey, and we observed 3 species in the city of Calgary over these 3 years: boreal chorus frog, wood frog, and tiger salamander. We did not observe 3 species that have historically been here: the Canadian toad, the western toad, and the northern leopard frog. The results, we took the results from these surveys, and we were able to do some occupancy modeling with the help of the Calgary Zoo. And we were able to identify terrestrial landscape variables that are important to the occupancy of amphibians. You'll notice I said terrestrial, and amphibians are aquatic and terrestrial species. We do not have aquatic data at the scale of the city to enable us to understand the aquatic component of our system. So that's a big data gap in the city of Calgary. However, through the terrestrial variables, we were able to create on the right there, the map showing you where the core habitat is for, in this case, wood frog. So as you're going from light purple to dark purple, the dark purple is increasing habitat quality. So those dark purple patches are showing you where the best terrestrial habitat is for wood frog in our city. So the key findings from this Call of the Wetland program were that we still have 3 species remaining in the city of Calgary, but we have lost 3 that were historically here. Most of our amphibians are occurring around the outskirts of the city where we still have wetland habitat. I think that is not surprising to many of you. And something that we really learned throughout this project was that if we want to continue to make, if we want amphibians to continue to make their home in Calgary, then we need to maintain the natural habitat around the wetlands, that terrestrial habitat that's so important. And we need to ensure that they can move between wetlands. So that brings us to the next project, which was, well, how are they moving between these key habitat patches in the city of Calgary? So we had an advisory committee for this project made up of City of Calgary staff, the Calgary Zoo, and the University of Saskatchewan. The picture in the center is one of our survey wetlands that was developed just before we started the Call the Wetland program. And I think most of you that live in Calgary know this is a very common site. We are still removing wetlands at quite an alarming rate. The objectives of our connectivity program were to map the core habitat for wood frog, boreal chorus frog, and tiger salamander, to map connectivity between probable movement pathways between the wetlands, and to identify what we're calling, from a biodiversity perspective, keystone wetlands that are important in maintaining amphibian habitat and wetland corridors. Now, I put this in for all you people that are really interested in the process and the modeling methodology, but I'd like you to focus on the products on the far right. And so we used those results from Call of the Wetland to develop habitat suitability models, which identified our core habitat. And then we wanted to understand, how are the species moving between the core habitat? So that's the second product down, the connectivity models. We used an open source program called Circuitscape. And to run Circuitscape, you require two products. You require the patches that you want to move the animals to and from, and you require a cost surface, which is a grid that tells you how easy it is for the animal to move through each grid on its way to the next patch. Circuitscape runs the model to determine a series of random walks between your different patches. And so it helps identify where the best places are for movement on the landscape today. We did a lot of other things as well. I'm not going to have time to go into those today, but happy to share the report or talk to you about it later. So this is the result just for wood frog. Remember, we did 3 species. I'm showing you one very simple model just to give you an idea. It is at the scale of the city, so it's hard to see exactly what's going on. But this summary is kind of that connectivity is still occurring in where we have a large riparian system still intact, so Nose Creek, Beddington Creek, Fish Creek, or along the outskirts of the city where we haven't developed, or along our big transportation corridors like Stony Trail. But what's really interesting is when you zoom in on these maps, please look at the one on the left. It's actually the northwest, not the northeast, as the title says. And what's interesting here is the blue is showing you where you still have connections between the wetlands. And you can kind of see that as soon as you hit major crossroads, so we have good habitat along some of our big road systems, but as soon as you hit the crossroads, we have a barrier. So we've got kind of these little isolated patches of habitat and connected habitat for amphibian species. So our main findings from this project so far, and we're still working on summarizing the results, are that the connections are mainly occurring along our major roads. And remember, we didn't look at the quality of that habitat along the major roads from an aquatic perspective. But from the terrestrial perspective, we still have connections along our major roads, but as soon as you hit crossroads, they're acting as a barrier, and we're not providing them with an opportunity to cross those crossroads. Habitat predominantly still occurs around the edge of the city or along some of our major riparian systems. And we have very few examples where we actually consider wetland connectivity in our planning for new roads or developments. There's a great example where the City of Calgary recently put a road through the Pritis Slough, and they actually put a big culvert in the middle to enable hydrological connections still. So that's seen as a great example of trying to mitigate or enable the connections in the landscape from an ecological perspective. Guy and I would like to thank the following Alberta Innovates and the following funders and supporters for supporting the 4 projects that we presented today, and look forward to the discussion and hearing the rest of the speakers. Thank you so much.
Thank you, Guy and Tracy. Great presentation. Now over to Corey Alberts, who will be speaking on his project, Saddle Ridge Stormwater Kidney Retrofit Project.
Thank you, Vicky. Can you hear me? Okay, good. So, thank you very much, everybody, for coming and attending this presentation. I'm delighted to be here, and I hope, Guy and Tracy, that you might be able to see some hope on the horizon for opportunities for wetlands and amphibians and things like that, because that is a key focus for us, is to create habitats within the city for all sorts of biodiverse environments like amphibian habitat. So perhaps we'll connect at a later date on that. But The project I'm dealing with is called Saddle Ridge Stormwater Kidney Retrofit Project, and it's something that we're very grateful to Alberta Innovates for having provided funding on this. I'm presenting on behalf of TrioVest Realty Advisors, who are the developer of this particular site. And without further ado, let's just get moving. So the problem case that we are trying to work through is that ongoing urbanization kind of creates stormwater. Prior to urbanization, you've got soils and all sorts of materials in the landscape that absorb water, rainfall, and we don't necessarily have a lot of runoff. But urbanization creates a massive amount of additional runoff. And we need to better use and preserve that water, because if we don't, it causes enormous stress on small water courses like Nose Creek, Fish Creek. And that's just in Calgary. You know, every community in Alberta or around the world has the same problems. But for us to better use water, currently it's a problem in the South Saskatchewan Basin because technically it's closed to new water licenses, and we can't actually use the water even if we make it very high quality because of this restriction. And we're hopeful that that's going to change sometime soon. But the fact is that we still have to move forward with generating a systemic approach to treating water so that it is higher quality, not just for community uses, but environmental uses. So we need inexpensive and simple solutions and it has to be a win-win for municipalities and developers. We can't have a developer-focused solution that causes terrible problems for municipalities, or vice versa. We can't have one that is focused on municipalities and basically costs an enormous amount for developers. We have to have something that addresses both, or else it's simply not going to be successful. And ideally, climate change resiliency is a key part of it. And we are doing actually both of these: win-win for municipalities and developers, and climate change resilient. We also need safe water. And in this case, safe water, I'm talking about low human pathogens, because we simply won't use what we don't trust. That water has to be safe for use as spray irrigation on the landscape. People have to be able to be exposed to it without a high risk of becoming sick as a result. And sick is different from human pathogens compared to having low levels of other contaminants that are chronic exposure. It's the dangerous acute exposure of single time from pathogenic organisms in water that is the real problem. And we need reliable produced water. At least 16 weeks of the year, we need some practical use of the water. It can't be just a day or two at a time and then weeks without it. That's not going to be a practical solution. So what we've come up with is we've called the stormwater kidney. And I'm going to talk about two different kinds of operation here. One is normal operation, and the other is storm event management, which is only occasional operation. Now that may sound strange because it's a storm pond, that normal operation doesn't actually involve storms. But think of it. You have a storm and then you have days or weeks between storm events. So normal operation for a storm pond is not having a stormwater inflow. And that's where we can take advantage of these large amounts of time and the opportunities to engage in biological processes to cleanse water and make it usable. So in normal operation, we take water from the main pond body in the center, and we pump it up to an elevated area where it flows through a treatment wetland horizontally first, and then into a vertical flow biofilter. And then in the vertical flow biofilter, we go down vertically through a granular media, and we can extract water and harvest it at the bottom. And that's the highest quality water in the whole facility. This is where we expect the human pathogen counts to be quite low and acceptable for direct irrigation without any further treatment. And whatever we don't harvest from the bottom, it simply gets circulated back to the main pond body, going through a variety of ecological habitat zones that we create and construct, so that we're constantly cleansing that water. Now, and we still have to be able to manage storm events. So the point is here, we have stormwater entering the sediment clarifier, and coarse particles settle out in the clarifier. And the key thing here is that we need to extract all the particles that could otherwise smother the sensitive ecological environment that we've created. Now, we can't take out the very fine particles in the sediment clarifier, but that's okay, because fine particles in turbid water is exactly what wetlands are well designed to provide cleansing functions on. That's okay. We just can't smother them with the coarse particles. And we have a number of successful antecedent projects that we've constructed over the years that have informed all of this process. And these are just good examples. And, you know, Guy and Tracy, I hope you can imagine that these would be just fantastic amphibian habitats that we're actually creating in constructed environments. So this type of a process and approach works for both new development and retrofits. You know, I'm here to talk about the retrofit opportunity, but it's easier to sort of tell the story of what it's supposed to do if I show you what it is in terms of new development and compare, you know, a thought exercise of what you would do in a new development situation if you take a conventional approach compared to a stormwater kidney approach. Now, I've got two images on the screen, one being conventional pond on the right and stormwater kidney on the left. I want you to understand that these are more or less in the same, well, in exactly the same footprint for the land that would be allocated to it in a development. So I'm doing this to show that in this exact same land allocation, what would we do in a stormwater kidney compared to a conventional pond? And even though we have way more open water on the conventional pond on the right, you may be surprised to know that on the left-hand side, the stormwater kidney can store far more water than the conventional pond and offers a great deal of other benefits that reduce cost and make a desirable space for people to engage in and habitats, all within the stormwater kidney. So how can we create more storage in the same space? It's basically, we're taking advantage of the fact that ponds have two types of storage. One is active storage and the other is passive storage. Passive storage is basically what's sitting there between storm events when there's a week between storm events. That's what's left over in the pond. Conventional ponds have a large amount of passive storage, and we've recognized that passive storage is actually not being well utilized between storm events. So what we've done is utilized this low power recirculation pump to draw water from the passive storage environment, pump it up to this treatment environment so that we can harvest that at a very low rate, which allows over the course of a year to fully manage all of the water in the pond. So we're creating a lot more active storage by having a much greater vertical range of water surface elevations, and dramatically reducing the amount of passive storage in the end. So I've got the illustration of cross sections here and some numbers on total excavation for each. And long story short, the stormwater kidney has, in this example, 30,000 cubic meters less total excavation, even though it has 30,000 cubic meters more of active storage compared to a conventional pond. There's a number of other benefits that play into the dynamics for developers and cities, but another time, we don't have the time to go through that. So the Saddle Ridge retrofit project on the left, this is what is proposed for 2020. And on the right is what was constructed in 2016. So this is a retrofit of an existing pond that has been constructed, commissioned, and is operating. Now, the idea here is that we have an open water body 1 and 2 And we will be pumping water from the body 2, which is basically floats at the same water level as 1. We pump from 2 up into the elevated space of 4, and then it flows along through there as an opportunity to have nutrients extracted and things of that nature, and then it flows into this area labeled 5. That's where the vertical flow biofilter is. And at that point, we have the option to either extract water from the bottom via what is labeled 6. That's an irrigation pump. And when that pump is operating, it extracts water from the bottom, and then it sends water vertically down through that granular media in 5. But if we don't extract any water from 6, then it simply passes over top of 5 as though it's like a horizontal flow wetland, and on, so that we can extract water from point 7, which has not gone through the vertical flow biofilter. But this is the dewatering location where we're extracting water to send to the outlet, and that's where we draw the water level in 1 and 2 down below what we call the gravity normal water level. And gravity normal water level is exactly what the pond is operating on right now. But we have the opportunity to draw the water level down to what we call the pumped normal water level. And that's where we gain all this additional storage. Pumped normal water level is drawing it down far below what it would be if we don't have the pumping system. And we're able to manage the nutrients in here much more effectively. So grading was completed in 2019. This is a photo I took in March of 2019. And planned for 2020 is the underground infrastructure construction of pipes and all the pumping systems. Plus, we're going to be doing pathogenic organism removal testing, and that's going to be done by the University of Alberta School of Public Health. So the key benefits here: low cost maintenance, low cost to build. It actually, we're finding it typically costs less to build these than conventional ponds because of all sorts of reasons, not just the lesser excavation, but also the size of the outlet pipes get dramatically smaller, and they don't have to be as deeply buried. Low-cost maintenance, because it's more or less a natural system that once you establish the plants, you just let it sit. It becomes more or less a completely self-sustaining natural space, full of amphibians, Guy and Tracy. So low power, off-the-shelf recirculation pumps is what we're using. And when I say low power, for some of our systems, we're using no more power than the type of fountains you might see in the middle of an existing storm pond. This is the kind of low power we're talking about. So it's really, truly recirculation. It's not, high capacity lift station type pumps. We do not use chemicals, and we are able to achieve water treatment that provides ecological and aesthetic value. Now, this last point is interesting because normally when you have a treatment system, you think of it being maintained by water treatment plant staff. Well, that's not the people that maintain this. It's people with landscaping skills. It could be landscaping contractors, gardeners, things of that nature. These are the people that maintain this type of treatment system instead of being highly trained water treatment plant staff. Now, here, the next one, low human pathogens in produced water. That is a key benefit, and that is critically important to making sure that we're not requiring the type of skill sets for water treatment plant staff. University of Alberta School of Public Health is going to be testing the system in September 2020 to ensure that we can make the type of claims that we hope are acceptable in stating that we can produce irrigation or human recreation contact water directly from the harvest point at the bottom of the vertical flow biofilter, even if up to 10% of raw sewage enters the storm pond in the incoming stormwater. Now, these are lofty goals, but we believe it's very achievable, and that's what the testing is supposed to bear out here. The testing is partially funded by the Alberta Innovates funding here. And we have increased storage, flood and drought resilience. What we're finding in all these projects that we're working on is an amazing increase in flood and drought resilience. The low flow water harvesting for very long periods of time, it's not just for human use, it's also for environmental support. We can create the type of low flow environmental support conditions that are beneficial for wetlands and other things. Or we can use it for irrigation or community fit for purpose uses. Now, these new projects, I'm just showing 4 here, we have others, but all of these projects came after we started this project and got the funding with Alberta Innovates for the Saddle Ridge project. So these projects may not have come about in this way without the funding by Alberta Innovates. So thank you, Vicki. This has been a wonderful opportunity for us to provide leadership in this environment. And so on the left, the image there is one that we have going in Chestermere. We had Qualico was the developer partner there, and we have a partner in Magna Engineering Services for the engineering part. And in the middle, we've got a couple of Brookfield projects also being done with Magna Engineering Services and LBC Consultants. And on the right, we've got, so the middle ones in Brookfield are both in Calgary. And on the right, we have a Cooley Ridge project, which is in Medicine Hat, and that we're working on with George Harris Collaborative on the environmental design and landscape architecture, and Sheffer Andrew. All these are turning out to be wonderfully innovative and exciting projects. And quite frankly, these may not have been at all possible without the support from Alberta Innovates. So it has been wonderful working on these projects, and I'd be very happy to take any questions when the time is right for answering questions. Thank you so much for the time, contributing time to see these presentations. And I will turn it back over to Vicki. Thank you so much.
Thank you, Corey. Really exciting to see the new approach to stormwater design, something that has seen a lot of change in the last little while. Just a reminder, there's the Q&A box. You can enter your questions. We'll have a Q&A session at the end for all of the speakers, so keep sending in those questions. Also, the chat box is there to discuss the topic of the session. Now I'm going to pass it over to Edwin Say. He will be speaking on his project, Assessing Water Connectivity in Rural and Urban Watersheds for Improved Water Management.
Thank you, Vicki, and thank you all for being here for the presentation today. I'm so excited to talk about this new project that Alberta Innovates is supporting on basically the hydrology of rural and urban areas and understanding the connections between groundwater and surface water systems. I'm talking on behalf of a team of researchers at the University of Calgary that includes myself, Drs. Masaki Hayashi, Jennifer He, and Angus Chu. We have a couple of MSc students already started on the project, Sean Elliott and Sam Johnson, and there'll be several more graduate students and postdocs working on this as well. We're incredibly delighted to have a group of partners, a diverse group of partners on this project, everything from government agencies, municipalities, other community groups. And in fact, our like I said, it's a new project. So our first steering committee meeting is going to be tomorrow. So we're looking forward to talking with them and getting more input and listening to their guidance and direction on where this project should go. So our hope is that the project in a nutshell is basically trying to support sustainable water management by understanding all of the connections between surface water, and with surface water, I'm including stormwater in that, between surface water and groundwater in both rural and urban settings. So that's the what we're looking at. Like I said, it's a new project. We're getting started this summer. Unfortunately, because of all the COVID issues, we haven't been able to get out there yet, but we're ready to get started very, very soon. It's a 3-year project. Will take place in and around the city of Calgary within the Bow River Basin. And we're really trying to leverage wherever possible existing studies or existing research. So for example, on the bottom right-hand picture, here you see a facility in the town of Okotoks. This is a bioretention research facility, and I'll talk a little bit more about that later in the presentation. The drivers for this project are varied, but it really comes down to intensification. Increasing population and urbanization is putting pressure on water resources. And that pressure is being responded to as we try to develop water management plans. How do we do that in an appropriate way? How do we develop resiliency to floods and droughts? So for example, in the bottom right picture, that's the 2013 flood in Calgary. And we know in urban settings, we tend to be prone to this flooding because of the differences in hydrology between that and a rural setting, as you see in the top right picture. And so there's hydrological knowledge gaps that we need to fill there. We also are looking at this, of course, in the face of climate change and land use change. And especially in the urban setting, it's a drastic change in land use. So a lot of urban environments are moving towards low impact development, and I'll talk about that, explain that a little more later as well. So the fundamental basis for a lot of this work is the water budget or water balance. So we know in any system that we define inflow minus outflow will equal the change in storage in that system. So for example, for a groundwater system, that might be groundwater recharge coming in, groundwater pumping, leaving, groundwater discharge, going to a stream or river, and the balance of those is the change in storage, which would be reflected in a water level change. And throughout those systems, we have intimate connections between groundwater and surface water that are very important for us to understand. And they can be quite complex. So in this diagram, for example, we could do a water budget at a smaller local scale in a recharge area. So balancing precipitation and evapotranspiration. Some of the water coming down might infiltrate, other water might run off. And if that infiltration extends past the root zone, it might become groundwater recharge. If we look at the other end of the spectrum, sort of towards the right-hand side, we might have groundwater discharge to a stream or river that supports base flows, supports the ecology in those systems, as we've already heard. But we often think of them in relatively simple terms as it's just groundwater discharge coming in. But there's a lot of variability. There's variability spatially. The same stream might be gaining water in some parts of it and losing water in other reaches of the stream, or it may vary temporally through the seasons, gaining it some parts of the year and losing it other parts of the year. So we need to understand those connections throughout the system. And then, of course, if we layer on top of this an urban environment, so the increase in urbanization adds impervious surfaces like pavement, sidewalks, the roofs of all the buildings, that decreases the amount of infiltration, increases runoff potential, results in flashier, what we would consider the stormwater responses. So again, it's important to understand all of the connections between surface water and groundwater at all points in the system if we're going to truly deal with these sorts of systems. And one way that people have been dealing with them is with low impact development. And really what that is, it's a strategy to improve stormwater management by trying to mimic the natural environment, by reducing those impervious surfaces, by promoting the movement of that water infiltration into the subsurface, vegetating these areas so that you get increased transpiration. And of course, that might provide some level of water treatment. So there's a water quality benefit here as well as an ecological benefit. And there's a variety of approaches. So the bottom example diagram here is just what you might consider a bioretention or rain garden type system, but there's other designs, green roofs, permeable pavement, and so on. In this study, we're going to focus mainly on bioretention and rain garden type systems, and they can be quite aesthetically pleasing pieces of the landscape as well, as you see in the photo for Marlow Place. And the way these systems are are supposed to function. This would be a typical bioretention design from the City of Calgary design guides. And again, we're taking that runoff, that stormwater runoff, coming into this lower lying area. It's going to move down through this growing media or this soil into the subsurface layers. And if they're not lined, there's the potential for them to then make their way all the way to groundwater. And again, we want to understand those dynamics, because what we're really doing is, like I said, we're mimicking a natural system. So there's a really good analog between previous research that we've done on, in the left diagrams here, this is research that we've been looking at groundwater recharge in the prairies, also funded by Alberta Innovates, where we're looking at often snowmelt dominated systems. So the snow accumulates on the landscape, melts in the spring, collects in the depressions, which we all see in the prairie landscape. So this is due to the glacial sediments that we have here in Alberta. And where that water is going, again, is just the water budget, this balance between precipitation, evapotranspiration, and runoff. As it collects in the depression, it can infiltrate and become groundwater recharge. It can also move laterally back in the landscape to sort of upland areas. So we need to understand that water movement. And we think we have a pretty good handle of how that works in a natural system. But these bioretention areas are a really good analog as well. So on the right-hand diagram, you see a bioswale in the town of Okotoks. And again, water's collecting in that depression effectively. It's making its way into the subsurface, infiltrating. And at that particular site, we're looking at the influence on groundwater, but there's also the potential for lateral subsurface flows as well. So we need to be able to understand and quantify all of these processes. So to come back to the larger project, our key objectives are sort of broken down into a number of tasks, and those are sort of laid out here. It's understanding hydrological data in urban and natural systems, understanding the linkages between surface water and groundwater. That's the key. A lot of the work in previous studies has looking at LID systems is focused on lab investigations. We want to focus on the field. Again, in the Alberta landscape, in our cold region context, we think frozen soil processes are going to be important, so we'd like to investigate those. Looking at the hydrologic performance of these systems and their impact on groundwater, again, both from a water quantity and quality perspective. And at the end of the day, translate that knowledge into useful assessment tools, hydrologic assessment tools, so people can predict and understand and make decisions on what's happening based on water flow and water quality. And throughout this, really try to engage a diverse set of stakeholders and make sure that the knowledge we're generating is of a benefit to the entire province. So the approach, the research approach that we're going to take is sort of twofold, two parts. The first part is, like I said, field-based studies. So we're trying to understand the important hydrologic processes. So here's some examples of the different things and that we would look at: evapotranspiration, soil moisture sensors, runoff, precipitation, stream flow, snow surveys, so on and so forth. And again, identify the key processes using multiple lines of evidence, and where possible, leverage existing research facilities. And I'll talk about some of those sites that we already have in a second, as well as build new ones where needed. So then once we've developed our understanding of those important processes, then we want to work towards developing appropriate models at all scales. So on the bottom, for example, you have some small scale modeling that one of the MSc students has already been doing. This is for an LID system or a bioretention system in Carberry Park in Calgary, and looking at water movement through this system, how much of that water can make it below the system as deeper groundwater recharge versus lateral flow. So we can investigate at the scale of an individual, say, depression, let's call it, versus the diagram in the top right-hand corner is a three-dimensional groundwater flow model of the entire West Nose Creek, which was developed in some previous work. So we'd like to look at that range of scales. And at the end of the day, it's not just about creating a model, it's about creating practical tools. So we hope to translate those model results into practical tools that stakeholders can actually take advantage of. In terms of the sites for investigation, I mentioned we're looking at a number of areas in and around Calgary. So in the rural area, we're going to focus on West Nose Creek to the northwest of Calgary. That's the blue area on the map. Of course, within the city of Calgary, we have a number of bioretention sites, and I've just highlighted a few of those specific locations. And like I said, so trying to understand that transition as water's flowing from, say, West Nose Creek in the northwest in that more natural area through the city of Calgary, and what the impacts are. So we have on the diagram on the right, you see a bunch of monitoring stations and historical information that we have available to us. We're also really excited to have another facility down in Okotoks, the Okotoks Bioretention Research Facility, which is shown to you on this slide. And it includes two main components. So the larger component you see on the right-hand diagram, the green areas are the bioretention system itself. And what that's doing is it's collecting water from a parking lot to the north, the sort of lighter green area, as well as rooftops from some buildings, the blue area. That storm water from those areas collects in these swales, moves its way through the system, and eventually gets conveyed to the larger bioretention system to the south. The white dots on there are monitoring wells that we're using to monitor groundwater in the system. So again, we're trying to understand what the connection is between that stormwater runoff and the groundwater system. The photograph that you see on the right-hand side is a photograph of the bioretention cells. That's the orange rectangle on the diagram. And these are smaller cells, a series of cells that were created, each about 2 meters by 2 meters by about 1 meter deep, filled with bioretention media, 3 different types of growing media, in fact. Each cell's fully lined, so we can do a water budget on it, look at water inflows, outflows, look at water quality flowing in and out as well. Each cell has different vegetation types, so there's 3 different vegetation types, plus a control, non-vegetated. And again, we can monitor soil moisture, temperature, look at local meteorological conditions. So we hope to leverage that facility and do some really interesting work on bioretention design. As I said, we're going to investigate multiple scales. So this is an example from the bioswale, in fact, at the Okotoks facility, where we have monitoring in place, soil moisture probes, a meteorological station, groundwater monitoring wells, again, to look at the full water budget and try to understand how much of that water is making it down to the water table and how much mounding would occur and so on and so forth. That's, again, at the scale of it, let's say an individual site. We're also hoping to, like I said, upscale that to an entire watershed. So on the left-hand diagram, I'm just showing you a transition from the rural to urban interface. And you can see how stark that contrast is. So as this is a Google image of, on the left, of West Nose Creek flowing into the city. And you can see it goes from a predominantly natural landscape to a heavily urbanized landscape quite quickly that has obviously a lot of development, a lot more impervious surfaces, stormwater management systems are in place there. So it'll be important for us to try to understand how that transition changes and what that means for things like stream flow, permanent versus non-permanent streams, wetlands, and the like, in both that as we transition from sort of an pre-development to developed condition. On the right-hand side, we've got a diagram of some citizen science that's been occurring. So this is the Rocky View Well Watch, and it's a series of landowner wells monitoring groundwater conditions, again, throughout this landscape. So we have access to that, and we've been involved in that previously. So the idea is to leverage as much existing information in these areas as we can and help us to, again, predict the hydrological processes that are occurring. Based on previous work, we think seasonality is important. A lot of the studies on LID and bioretention designs have been done in more temperate climates. So we want to focus on the climate of Alberta, which we know has a lot of seasonality. And that work, like I said, has often focused mainly in the summer period. Whereas we think the winter and the spring period in particular are going to be particularly important in terms of water movement through these systems. So it'll be a full 365 days a year of monitoring these systems and trying to understand these seasonal processes and incorporate them into those hydrological models that I talked about. Within that, we think frozen soil is going to play an important role. We know it does in the natural settings. We've seen that. So, for example, the photograph here you see is the landscape just north of Calgary. And again, in the spring, where does that snowmelt partition do? Does it infiltrate into the ground? Does it flow laterally into a depression? Once it's in that depression, does it evaporate or does it infiltrate into the subsurface and become recharge? Part of this process, we think preferential flow is important. Macropores, which are just larger than normal pores, often created by root holes, desiccation, weathering, those sorts of features. And these happen and will develop through time in these bioretention cells as well. So what role do they play in all of this? So at the end of the day, the project outcomes are listed here. And on the left-hand side is mainly the scientific focus here. So understanding, like I said, hydrologic function, pre and post development, developing new tools and hopefully useful tools for trying to mitigate some of these development impacts, advancing our understanding of LID designs specific to the cold and arid region that we have here in Alberta. And at the end of the day, providing a scientific foundation for sustainable water management. That's really what we want to try to do. On the right-hand side, training and skill development, that's really about building innovation capacity in the province, making sure people have the skill sets that we're going to need to do better prediction in the future to deal with things like droughts and floods and changing climate and land use and all of these factors. And like I said at the start, interagency collaboration is really important. And again, I want to highlight the different groups that are involved in this project already. We want to engage the stakeholders. We want to engage the broader public and the community, try to encourage this interagency cooperation, whether that's through sharing of data, sharing of monitoring sites, whatever it is. And then again, at the end of the day, transfer the knowledge that we've gained to stakeholders in an appropriate fashion that they're able to use for their own decision making. So with that, I thank you so much for your attention, and I will pass it back to Vicky.
Thank you very much, Edwin. It's really exciting to see where the research is going, and it'll be great to get updates as the project progresses over the next 3 years. Thank you also to all 4 speakers. Really exciting to see the different perspectives that each project takes to advancing and supporting water management in urban areas. Really also neat to see the connection between the projects and how they support each other. So we'll move over to the question and answer now, and you can continue to submit your questions as we go through this part of the session. If we don't get to it, we will try and answer it later in email, so continue to submit those. We'll give Edwin a break here, and we'll start with a question for Guy and Tracy. The first question here is, DUC and ABMI announced in early June that they have collaborated on a 3-year wetlands mapping project for the entire province of Alberta. Will Mistacus be tapping into this new data once available?
So one of the components of this whole project was to look at the available data and assess its relevance to municipalities. So one of the challenges that we've faced in the past has been when data was created, what was it created for and who was it created for? So the way we're approaching that is a couple of different things. First of all, like I said, we did a catalog. The current ABMI wetlands data only covered about half of the, or about a quarter of the area that the Bow Basin municipalities cover. And then same thing for the Canadian Wetland Inventory that Ducks Unlimited maintains, where it's more opportunistic. So it has been patchy across the entire Bow Basin. And the Alberta Merged Wetland Inventory is a result of exactly that kind of thing, where we've got different pieces of data in different places. Some of it is new, some of it's old, some of it's high resolution, some of it's low resolution. So what we're trying to do is come up with a data set across the basin that would be consistent, so that one municipality talking to another municipality, one developer working in one municipality and then working in another municipality would have similar information and similar questions. So in the case of existing data and new data that comes online, so for example, a number of the municipalities within the basin already have their own wetland inventory. So in any of those cases, we use that data. We will use that data to relate to another question asking about whether or not the data set is available. It's not yet available. We hope that will be next March. But we use the existing data to train the models that are developed to output the 4 data sets that I just talked about. So we'll be looking to use any data that we possibly can, always gearing it towards the use by the municipalities. And the other piece of that is making sure that we're consistent with the yet to be released wetland data standards that the province of Alberta is just putting forward and making sure that we match with that. The other consideration here is the replication, the renewal rate. If it's an extremely complex and extremely expensive initiative, we know that it won't be updated very regularly. So in that whole consultation process, we tried to find out what would be a mechanism that would balance all of those things. And working with Sherry Clare from Fiera Biological Consulting, she came up with a methodology that does that balance using some existing data and gets us to that minimum mapping unit. So when new data comes available, like after 3 years, if there's a new data set that covers more of the area, we'll definitely use that to inform that data set.
Great, thank you, Guy. Question here for Corey. Please clarify where the human pathogens may be coming from in stormwater being used for the stormwater kidney. Is wastewater being blended with stormwater? Example, combined sewer. I understand that this is not being used in the city of Calgary.
Yeah, so the design criterion we're trying to apply here is to say that it's suitable for scenarios where you might have up to 10% raw sewage coming in. This is, we have to set that as sort of like a functional objective because the intention is not only to have new development, but also retrofit, and not only in Calgary, but in other communities in Alberta, Canada, and around the world. So the human pathogens, in fact, a lot of our focus right now is on how can we do something that is not only applicable in our home market, but is also applicable in other places like Mexico City or Philippines. These are places where I've been to on trade missions, and there's a profound need. And basically, there's no such thing as separate systems. There's hardly any separate systems. Almost everything is combined. So we're trying to develop a philosophy of design and operation that would allow for some pretty difficult and challenged wastewater to still be produced as high quality water. So it's a long story, but yes, in Calgary we don't have very many combined sewage scenarios, but you would be surprised that even though we think there isn't a lot here, there still are. And this is, some of the research that University of Alberta School of Public Health has been doing. And they still exist in Calgary.
Thanks, Corey. And I just add to that, some of the current research is showing that even if it's not a combined sewer, there's some leakage or unintended combination that's resulting in some pathogens potentially being in the stormwater ponds. So, yeah. So next question here, go to Edwin. Wondering about involvement of Indigenous communities and organizations. There could be some interest to contribute to the project, especially in Calgary, the local nations. Are you planning to include these perspectives?
Yeah, so let me just make sure I'm on. Yeah, sorry. Making sure my mic was on. Yeah, thank you very much for the question. So at this point, like I said, we're just kickstarting the project right now, and we're really trying to engage with all relevant stakeholders, and that would include Indigenous communities as well. We haven't specifically looked at aspects yet because we're in the initial stages of looking for opportunities and appropriate sites where we can do monitoring. And if there are communities that are interested, I would certainly encourage them to reach out to us, and we'd be willing to look at what opportunities are available and what sort of information that they would want to need from their perspective. Again, I want to emphasize that aspect, because what we've been told as an academic, we often focus on the research aspect and on the science side, but we need to really understand the community engagement side and how the knowledge that we're generating is going to be used. So I think that's an important piece in this.
Great, thank you. I'll go back to Guy and Tracy here. Besides wetlands, what other natural infrastructure are you working on?
I'll answer that one because I think it probably refers to the Municipal Eco Toolkit and the different elements of natural infrastructure. It's a good question. One of the challenges being everybody defines natural infrastructure, green infrastructure, natural systems, all very differently. So what we tried to do was help municipalities, first of all, with their determination of what are the natural infrastructure elements within their municipality and the natural systems that underlie that. So that will include obviously not just wetlands, but a variety of other land-based features and water-based features that would exist within a municipality. So escarpments, riparian areas, areas of native vegetation, infiltration zones, the sort of full range of infrastructure that would support certain types of benefits. So that's another part of that project, is to help municipalities draw that connection between there's the natural system element that has a function that generates benefits. So you might have, using the wetlands example, it has the ability to store water, but we don't, as a human species, care about that, quote unquote, from a flood protection perspective, unless that's storing water near a place where we're concerned about flood. So we're trying to help the municipalities work back from that, from the benefit that they're looking for. This correlates with another project that we're working on, where we're helping municipalities identify a mechanism for mapping their natural infrastructure based on existing GIS holdings. So in some ways, it's a translation process of taking all of those different elements of natural systems and making sure that you can get them in a GIS environment. What we're not focused on is the heavily engineered components of that whole discussion. So what's sometimes called the green infrastructure, where you are not maintaining a natural system that provides benefits, but you are mimicking natural functions, or you're creating systems. So we're not saying that that's unimportant. We're just trying to help municipalities in this step identify the tools that they can use to maintain those broad natural systems. I hope that answered the question.
Thank you, Guy. Go back to Corey here. If the design has relatively little passage, storage, depth volume, won't the passive storage volume tend to heat up more compared to conventional pond, possibly leading to water quality issues during extended dry periods?
Yeah, so when this is a very relevant question, and it's a natural question until you have an opportunity to see where we can take the designs that actually mitigate almost a whole host of common problems that happen in storm ponds. Since we have a very highly varied ecosystem in there, and we can put targeted areas where, tall trees like cottonwoods, we can have those in our pond. It behaves and functions and feels like a floodplain riparian area. So we can strategically place cottonwoods or other, relatively tall shade trees right close to the small open water bodies that we have remaining, and that provides all this shade for the open water. And in the areas where the wetlands, it's well known that all the emergent plants that are in the wetlands provide shade for the water that's in the wetlands. And when the water returns from our vertical flow biofilter back to the main pond body, it's going through willow groves and all sorts of diverse habitats. So most of this water, when we have extended periods between storm events, is actually shaded. So the amount of heat and heating that happens is dramatically reduced. So, but it takes a different way of thinking about the opportunities of how you can place these trees and shade opportunities in there that is that allows us to think a little differently about how can we mitigate not just this, but a whole bunch of other problems that are common in storm ponds.
While I have you unmuted, quick question, does the kidney have a liner? If so, is the liner a barrier between the kidney and the local water table?
So liner is something that is not required from a treatment perspective, but from a water retention perspective, of course. If you have underlying soils that don't allow for that water to be retained, then you put in a liner. Conventional storm ponds would have the same issue. You know, you have a liner typically up to normal water level. We might have a similar thing, but typically we actually have a lot less liner. We can even reduce the amount of liner because our area with permanent water is smaller than a conventional pond. So in other parts of the city here, we dig right into lacustrine clays. So basically you're digging into a liner. So you don't need to line it specifically if you're digging into the clays and natural native material that would not allow water to leave. So, but anyhow, yes, we would look to put a liner in to preserve water so that the whole system doesn't go dry.
I have a question here for all speakers. I heard climate change resiliency mentioned in the work of Mistakis, but how is it applied in the work of the projects we heard about today? Does everyone consider climate change in their work, and if so, how? Why don't we start with Edwin?
Yeah, so climate change is considered in the work. We're not specifically going to be investigating the impacts of climate change directly. So for example, with our modeling approach, we're not going to be looking at the modeling the influence of climate change. That comes as sort of separate from the focus of this particular study, although we are doing related research in those areas. So climate change is always something that we're looking at. This particular study is going to focus on understanding so that we can create better models that are more predictive so that we can understand the effects of climate change. But specifically looking at climate change for this study, we won't be doing that as part of the modeling.
Thanks. Corey?
Yeah, climate change figures very deeply in our thought process. In fact, this project we're working on in Medicine Hat has a very specific two-basin integrated system where one of those basins is part of the stormwater kidney. We're treating it as a climate change resiliency water tower. So it provides additional flood protection storage, but also profound drought mitigation storage so that the continuous circulation can happen in the arid climate of Medicine Hat for perhaps 3 months of bone dry baking heat. So we're storing that amount of water in this system for climate change resiliency. More or less, Ed Say's presentation was talking about LID, low impact development, and as a rule, low impact development installations tend to be relatively small or multiple sites around a community. Think of the stormwater kidney as philosophically completely consistent with LID principles, but it's at a community scale so that we have more water in there that's available to recirculate through that and provide drought resilience and a great deal of extra flood resilience too. So climate change is critically part of our design philosophy.
Great. Guy and Tracy, did you want to add any more on your approach to climate change in your projects?
I'll jump in and just say something quickly. So it was a key message in our citizen science program from an engagement perspective about why urban wetlands are important and why we should, an ecologically connected system is more resilient and why how that relates to climate change. But in the amphibian connectivity modeling, we didn't do any future scenarios. It was all based on present day. So I would say that it wasn't really included in that particular model.
Okay. Guy, I know there's a sub-question to another question you answered that was missed in terms of how you'll be making the wetland data available.
Yeah, sorry, I didn't mention that before. It's an important question. The data will be served out on a web-delivered mechanism. Anybody will be able to access that data. There'll be no paywalls or registrations or that sort of thing. And one of the things that speaks to is the accessibility of the data around the landscape. And there's a question about connections to First Nations. So we had some interest from a variety of different other people, federal lands, irrigation districts, First Nations, others who were looking at this municipally focused project and asking about it. And because the methodology is based on the entire landscape, it doesn't just stick to a quote unquote municipal boundary. That means that all of the reserve lands, for example, will be covered by this data set. So First Nations in the area will have access to information about the wetlands on their lands as well.
Fantastic. Thanks for adding that answer. We'll go back to Edwin here. A quicker question, are there effective modeling software to determine the performance of low impact developments like bioretention?
It's a good question, yeah. So I think the answer to it depends a little bit on the scale that you're considering. As Corey was talking about, an individual bioretention system is quite small. It might fit in your front yard as an example, or your backyard. So the footprint can be quite small, and there are tools available at those scales, certainly for simulating and predicting. And as part of a related project that Jennifer He is working on, that's one of the aspects that she's specifically working on, is trying to characterize the hydrologic performance of LID systems. When you move to larger scales, at the scale of a watershed, for example, within an urban watershed, that can be a little bit more difficult to predict, and it's often a different tool entirely, because the small scale tool isn't necessarily going to work and be too computationally demanding, for example. So you have to look at other tools. And that's why I said, in our particular study, we're going to try to look at developing how we might upscale, because it's really a fundamental consideration in all modeling. If we can't upscale and do predictions at a larger scale, at the scale of a watershed, it makes it difficult, but that's a very difficult thing to do. And I would argue that right now we probably don't have great tools for it. So hence there's a need for some of those assessment tools.
On a related note,
Vicky, sorry, Corey here. Can I jump in here for a moment?
Absolutely.
Yeah, and you're right on the scale. That's something that we're actually working on, is the watershed scale. In fact, this is entirely what our focus is. So we have developed the ways of modeling essentially the LID at a community level in the stormwater kidney system. And it's turning out to be extraordinarily effective. And we've been able to quantify how much water bypasses the system compared to how much is completely managed through this biofilter. And it's only a tiny fraction that is technically not perfect or ideally managed in the way we're looking to do so. So anyhow, happy to talk about that another time. But yeah, we're doing that at scale. That's our focus.
Sounds like a potential opportunity for you and Edwin to connect on that one. So continuing on the modeling question for Edwin here, could you please comment how preferential flow and freezing thaw processes might be significant moving from small to large scale watershed modeling in southern Alberta?
Yeah, that's a great related question. So again, at the small scale, we have a reasonable understanding. So preferential flow would be, in this case, for example, in a cold climate like ours, especially in winter, it's often considered that the ground is basically impermeable, like concrete, like an impervious surface. But we know from our field studies that that's not true. It's these preferential flow pathways that water can make it down through the frost layer and into the subsurface. So that frozen soil and these preferential flow paths are dictating how much of that water is going to infiltrate versus run off. And it's dependent on a number of factors. How much preferential flow there is, how wet the soil is another key factor. And this has important implications, like you said, as you move up in scale. So we can predict it at a smaller scale, but we're also seeing it in our larger scale hydrological models. And by larger scale, I mean at the scale of maybe the province or of an entire Bull River Basin. The tools that we have for simulating runoff and flow in prairie hydrological models are indicating that they're predicting much more rapid flow because of it's all running off the surface as though it was behaving as this impervious surface. And the soils aren't always behaving that way. So we need to incorporate these features into these models that will hopefully, again, provide better prediction moving forward. And it becomes important when we're talking about, I saw another related question about midwinter melt. So we have a Chinook climate here in southern Alberta, and we get midwinter melt events. So it's important not just for those spring melts, but those midwinter melt events, and then things refreeze again. So it's those pieces are all critical to understanding what's happening at the larger scale and what it's going to look like for larger watersheds.
Thank you. I'm going to jump back to Corey here and join two questions together. There's a question on how is nitrogen and phosphorus removed? And then general question on performance of removal of water quality parameters like nutrients, sediment, metals, and if you have any data.
So very relevant questions, and sometimes it's difficult to answer these questions with the type of answer that people are expecting and hoping for. How is nitrogen and phosphorus removed? Well, one of the key things that we're providing is essentially the type of astonishingly varied microhabitats throughout a biologically diverse and active space, so that nitrogen and phosphorus are simply nutrients that now are craved by all these organisms in there. Nitrogen gets removed through a combination of aerobic and anoxic processes, and that's all the incredible number of microhabitats that we're creating mean that there's ample variety of those type of spaces inside here, and by continuously circulating, we give an opportunity for the water to not just have a single pass through and only one opportunity to be exposed to these microhabitats of varying aerobic and anoxic. And phosphorus obviously is something that is a critical nutrient for organisms to grow, and we're growing all sorts of things, not just plants, but amphibians, birds. All these things are supported, their life processes and life cycles. So that is in there. Now, on other things, and I want to take you back just a moment to help you understand where my priorities are. And I made a big deal about the human pathogenic organisms, because in our view, all of these other nutrients are important to control, but they all pale in comparison to the need to control human pathogenic organisms. High nitrogen, high phosphorus, or even elevated metals levels in this water, they're important to control, but they cannot produce anything more than a chronic risk, which means multiple exposures over long periods of time are the things that can cause potential problems. Now, I'm not trying to trivialize that. I'm not trying to dismiss the importance of that. But compared to human pathogenic organisms, if we're not controlling those, then a single exposure can cause, a great deal of problems for people and death. So in the developing countries that we're working in, our focus has to be critically and almost exclusively on human pathogenic organisms removal. And the presumption there is that by doing a great job there and creating an enormously diverse habitat that can control these pathogenic organisms, we will, by default, also be creating an environment that will be effectively removing these nutrients and other contaminants. So do we have data on it? No, not the way that you would be looking for, but we're using simply an environment that craves all these nutrients and is well known in generalities to be able to even take out some metals and things like that, and contaminants of emerging concern like pharmaceuticals and things like that. So anyhow, I won't take up more time, but it's a really nuanced answer to some really important questions.
Thank you. We could do one last quick question here for Edwin. Would you be interested in expanding your monitoring research to Edmonton, where soils and climate are different?
The real short answer to that is absolutely yes. We want this to be province-wide. We think it's important that we understand them, and certainly Calgary and Lethbridge and Edmonton each have different climates, but they've also got a lot in common between them in terms of how they function. So we're focusing in and around Calgary because, well, first of all, that's where we're physically situated, gives us closer access. It's also where a lot of our historical work has been done. But if there were sites and situations in Edmonton that were relevant, we would certainly consider it.
Great. Well, thank you, everybody. I'll wrap up the Q&A session there. Thank you so much for attending. Thank you to our speakers. This was the first of our monthly Alberta Water Innovation Connect series. Really excited for the next sessions. This session has been recorded, and the recording and slides will be made available. We will be sending out a short survey to all attendees to get your feedback. As I mentioned, this will be a monthly series. We want to continue to improve and make sure that these sessions are meeting the needs of our audience. The next session is on planning for Alberta's water future. It'll be July 29th, so put that in your calendar and you'll see invitations for that going out soon, as well as an update and registration link on our website. So thank you again, everybody. Really appreciate this. Looking forward to the next session. Enjoy the afternoon.